So this is the CS643 Group 5 paper presentation for the Daniel Firestone paper titled BFP, a virtual switch platform for host software-defined networking in the public cloud. And I'm George Dacca,
I'm Johnny Ortiz.
and let's get started. So a little background on Azure, officially known as Microsoft Azure. It's Microsoft's public cloud computing platform. It's one of the leading cloud service providers alongside competitors like Amazon Web Services, AWS, and Google Cloud Platform, or GCP. It provides a wide range of cloud services, such as cloud computing, analytics, storage, and networking. And users can choose and configure any combination of these services to create and scale new applications or run existing applications in the public cloud. And so the main focus of Azure is scalability, because a lot of their clients are enterprise clients who need large applications, changing needs. It also focuses on performance, availability, and fault tolerance. So this chart shows the number of active Azure users. You can see in 2017, we have 715 million active users. And as of the last year, there are over 722 million active users. So their technology solutions are going to need to be scalable enough to handle such a massive number of users and requests.
So the growth of public cloud platforms like AWS, Azure, and Google Cloud has led to a new era of data center computing. These platforms manage millions of servers, and their challenges are not just about the scale. So the motivation of the paper was the need for a more flexible host SDN platform that could provide flexibility, scalability, and performance. So what is software-defined networking? This is the default standard for setting up network infrastructure in modern data centers to network management. It enables dynamic, programmatically controlled network configurations by separating the network control plane from the forwarding control plane. And a single SDN controller can manage an entire network. So this can result in simple routing decisions and policies. SDNs are implemented because the functionality of hardware can be done in software, therefore enabling rapid adaptation to changing business requirements or network conditions. Normally, SDNs are leveraged using open protocols such as OpenFlow, which allow to communication between network devices. And some of the benefits for the SDN approach are faster service delivery, reduce costs, and improve network performance and monitoring. So some of the related work that the authors mentioned was being used at this time was the VL2, which was introduced in a research paper by Microsoft. And this was influential in shaping the modern data center network designs because it created virtual networks using stateless tunneling. And also they mentioned the Ananta, which was a scalable layer 4 load balancer. In the paper, it also discussed the current available open source solutions such as OpenFlow and OVS. OVS is an open source virtual switch implementation of OpenFlow. The paper highlights the design differences between VFP and open source projects like OVS, emphasizing the unique constraints of public cloud environments. So the authors of the paper had the following requirements to solve. They needed a flexible SDN platform that could provide rich network features. And these features were private virtual networks with custom address spaces, L4 load balancers, security features like access control lists, virtual routing tables, bandwidth measurements, quality of service mechanisms, and more. And the reason also is because they needed to solve the scalability, because traditional hardware routers are not economical for implementing complex policies at a massive scale. And a common solution for the SDN problem is the use of virtual switches. Uh, they operate on the virtual machine hosts. It sits on the host machine, manages the connection between the connections of virtual machines to the network. It offers scalability. As the servers increase, the virtual switch scales accordingly, ensuring the physical network remains simple and fast. And it can also be tailored to specific needs. So what is a virtual switch? Virtual switch is a software program that enables a machine to communicate with another, and it connects virtual machines in a similar way as physical switches. Um, Virtual machines use virtual switches and virtual networks adapters to connect to physical networks. So Azure, being a leading cloud provider that heavily leverages host-based SDN, um, introduced the virtual filtering platform because they needed to come up with a solution to the design of the virtual switch where it could be programmable by enabling it to support diverse requirements and configurations. You also needed to meet the demands of cost-sensitive and performance-hungry cloud workloads. And that is when they introduced the virtual filtering program, which the name comes from its function where it filters the traffic for each individual network interface card, allowing controllers to dictate the SDN policy. Some of the key attributes of VFP is that it runs on all Azure hosts, so it's present everywhere in Azure. Um, It is designed to be both highly adaptable and performance driven, giving it a dual purpose. And Azure's VFP is an example of how virtual switches can be designed to meet the dual demands of cloud scale environment by providing flexibility and performance. So as we mentioned before, some of the existing solutions were open OVS, and this is widely recognized for its role making programmable host network more accessible. OVS supports OpenFloor, and by enabling deployments to manage both virtual and physical switches via the same protocols. However, despite some of these benefits, there's some limitations that were highlighted in the paper. Number one, it doesn't support true independent multi-controller models. It doesn't support stateful actions like NAT or its MAT model. The VTEP schema in OVS is not flexible enough to handle the VL2 style VNets without changes in the virtual switch itself. And OVS does not scale to support large VNet effectively. So therefore, OVS lacks the generic offload action language, making it challenging to support certain complex operations efficiently. So the design goals for the VFP was to provide a programming model allowing for multiple simultaneous independent network controllers to program network applications and minimizing cross-controller dependencies that allows controllers to define their own policies and actions rather than implementing fixed set network policies for predefined scenarios. It also provided the match action table, or MAT, programming model capable of using connections as a base primitive rather than just packets, stateful rules as first-class objects. And working with connections rather than packets is more natural to programmers. And some of the benefits, it was that it allows frequent deployments and updates without requiring the reboot or interrupting the virtual machine connection, and allowing for strong service monitoring. Also to provide high packet rate, even as the tables and rules grow large, and implementing a more efficient way to offload flow policy to programmable NICs without assuming complex rule processing.
So now we're going to look at one aspect of the VFP implementation, namely how policies are implemented and work under the hood. So policies determine what network traffic gets in and out of the VMs. And this is useful for the admins of Azure to make sure, for example, people can't access other people's VMs and protect them from outside attacks. And at the highest level, a policy is a hierarchy of objects. An object can be a port, a layer, a rule, or a group. And the policy is composed of a tree of these four types of objects. So a port is the most basic unit that a VFP policy can filter on. A layer is a stateful flow table that contains the match action table policy. A rule is the match action table entry itself. And then a group stores and manages a collection of related rules. So each of these objects is assigned a priority value to determine the order that they're considered. And we'll see how that priority value is used soon. So starting off with a port, every port has match action tables that can filter traffic coming into or out of the virtual machine. And making this the most basic unit allows for controllers to manage traffic for different VMs independently, and only implement filtering on ports where it's needed. So some controllers might handle SSH traffic on port 22, while other controllers might be in charge of HTTPS traffic on port 443. So this makes the system more modular and flexible. So going on to layers, each port's policy is divided into layers, and a layer is just a basic match action table. A layer for a port can be created and managed separately by different controllers, as we just mentioned. And a layer contains inbound and outbound rules. So here is a nice diagram showing a packet coming in and going through each layer sequentially, and it matches with each rule based on the packet state from the previous layer. So controllers can specify the ordering of their layers with respect to other layers. So there's that independence that we talked about earlier, and layers can be created or destroyed dynamically. So we have a VNet layer, a NAT layer, access control layer, and a metering layer. So the packet's going to come in, go through each of these layers. And then, so if this is the traversal for inbound packets, for outbound packets, the traversal will be reversed. And so next we have a rule. So they perform actions on packets based on the MAM model. So a rule is essentially made of two parts. A condition list, which is just a set of criteria for matching a packet, and then an action, which is what to do if the packet matches. So more on a condition list, it has a type such as a source IP address and a corresponding list of matching values. So that could be a single value, for example, if you want to match with one IP address, or it could be a range of values if you want to match with, all IPs in a particular subnet. And what does it mean to match exactly? So for a condition list, matching just means any of the listed values. So that's an or clause. When you want to match a rule, so that means you have to match all condition lists in that rule. So you're anding all the condition lists. Next, we have groups. So rules are grouped into logical groups. And when processing a packet, VFP will iterate through all the groups in a layer and find the highest priority rule in each group that matches. And so each of those rules is going to have an action associated with them. So VFP will determine will select the last group with a matching rule when determining what action to take. So next we're going to talk about performance metrics of the virtual filtering platform. And one aspect is the encapsulation decapsulation rate, which refers to as a packet, for example, an outbound packet from the machine. It's got to traverse each of the layers of the OSI model, and as it is traversing each layer, it's going to be wrapped up in some additional metadata, whether that's from the IP layer or the transport layer. Each layer is going to append the packet with the appropriate header. And then, so that refers to encapsulation. Then decapsulation is the reverse, as it's being unpacked and the metadata is being removed. So that process, they're able to achieve rates of 40 gigabytes, per second on their NICs. And their classification algorithm has beat linear search performance by 1 to 2 orders of magnitude. And in general, they're able to achieve up to 25 gigabytes per second of bandwidth. And that is as of 2017, so this has likely improved since then. So some concerns about the system is that doing stateful packet processing as opposed to stateless may increase overhead and system complexity because you have to maintain that state somehow and maintain the state of the packet as it's being changed by these many controllers. So it can there's a concern that it could increase complexity. Another issue is that this is a closed source implementation, so advances to open source frameworks such as Open vSwitch, it's not going to benefit from that. And then multiple controllers being able to define sections of policies for one VM might make network troubleshooting a bit more complex. So it's really important for someone that's using a solution like this to have a set of best practices so things don't get messy and hard to debug.
So since the introduction of VFP in 2012, there has been 21 major releases, and it has been implemented across all Azure servers globally. VFP became public via Windows Server in 2016 for on-site workloads. This allowed multiple controllers have programmed VFP independently. All the connections to the data center are treated safely by VFP, and the definition of VNet and other policies have evolved without altering the VFP policies. VFP has had numerous updates without needing to be rebooted. It also introduced unified flow tables, and this provided a mechanism to optimize the speed and efficiency of network traffic that is processed inside the Azure's cloud environment. It also achieved this by offloading specific exact match flows to a hardware path for faster handling after the initial software-based classification. And VFP's classification algorithm surpassed linear search performance.
So, in conclusion, the authors have convinced us that this is a significant contribution to the field of software-defined networking and will further speed the movement towards cloud computing. Other solutions, such as those by Google, are built on top of OpenFlow or other open source solutions. Um, the authors have deployed their solution to Azure and ran it successfully for years using VFP. So the solution worked, and Azure's continued functionality is a testament to that. And the authors have appeared to implement what they stated as their design goals at the beginning of the paper.